Hello everyone, I'm very happy to be here today to present our work on auditing privacy-preserving machine learning. So privacy-preserving machine learning has emerged as a powerful technology designed to enable the use of machine learning in scenarios where data privacy and confidentiality are crucial. So for example, in settings where it's important to keep the model secret because it's proprietary to the organization, or when user privacy is a concern and we need to keep their queries private to protect sensitive information. Or in settings where we want to keep the training data confidential while still allowing it to be used for machine learning, such as when training a model on sensitive data contributed by multiple parties. And PPML achieves this by relying on secure computation techniques such as secure multi-party computation and fully homomorphic encryption, which at their core achieve the necessary privacy by concealing the input data during machine learning, inference, and training. So while this opacity is beneficial for privacy, it hinders the use of conventional techniques to audit machine learning models and their training data. And this creates challenges in meeting other important and often legally required objectives in machine learning, such as transparency and accountability. So to understand why, let's take a closer look at the PPML pipeline. So for inference, we can use private inference protocols to serve predictions to the client without disclosing any other information about the party's inputs. And for training, private training protocols enables parties to collaboratively train models without exposing their individual datasets. So we've seen a variety of works that augment various parts of this pipeline with additional checks and validation. So for instance, by checking that training inputs follow a specific distribution, by verifying predicates of the training algorithm, by validating the model on known test instances, or by performing inference time reliability checks. But while these techniques can show interesting properties, they are not suitable for more general and real-world machine learning issues that often only occur after systems are deployed. So for example, if we get an unexpected prediction, these works don't give us a way to go back and investigate why this occurred. And this comes up not only when trying to explain predictions, but also when we want to do things like investigate model behavior, find relevant training samples, or certify additional constraints on demand. And so in order to realize these kinds of functions, we need a separate auditing phase with an auditor, which in some works has been assumed to be a trusted third party, but could of course also be realized cryptographically. But now we have an issue of consistency between the phases because parties might maliciously alter their inputs to the auditing phase so that they no longer match their original inputs to training and inference. So we might consider solving these consistency issues by extending the multi-party computation to cover the entire pipeline. But in practice, it's generally not feasible to continuously run large MPC deployments with many parties because MPC protocols typically don't scale well in the number of parties, and it's complex to maintain a large amount of secret state over extended periods. So we really want to have separate phases consisting of smaller MPC computations, which is necessary not only for efficiency reasons, but also to support existing PPML pipelines with separate training and inference phases. And for both phases, there exists a rich and diverse literature of PPML frameworks, and each is tailored to different settings and threat models. And so we really want to be able to support this modularity, but then we have to solve this input consistency issue between the phases. So in this work, we propose a framework for auditing PPML that ensures consistency while being compatible with existing MPC protocols for training and inference. And the way we achieve this consistency is through this idea of succinct cryptographic receipts. And these are passed as output after training, and then at inference time, the client receives the receipt with their prediction. This receipt records all the material that is necessary to later verify the consistency of the training data, the model, and the prediction during auditing. And so as you can imagine, the succinctness of these receipts is essential for the performance of our framework, and we provide a new construction that allows efficient verification of these receipts in MPC. So let's take a more detailed look at our protocol and this receipt, starting with the training phase in which the data holders provide training data to the compute parties in order to train a model. So first, the receipt should contain a reference to the training data and the model, and so each data holder needs to create a commitment to its input. The compute parties then need to verify that these commitments were generated honestly, but the challenge here is that we have to do this over the secret shares. And so later I will talk about how to do this efficiently, but essentially this POC.check is a more MPC-friendly commitment verification protocol. So after we verify the inputs, we can train the model and commit to the output. So now we need to include some additional measures for the integrity of the commitments, because a malicious model holder could have generated these commitments on its own, and external clients would have no way to check whether the commitments are connected through some valid training. And so to ensure that the clients can verify this, the training computers sign the commitments using a distributed signature protocol. And then as a final step, we also include a signature for each data holder to prevent the other parties from forging input commitments on their behalf. So the inference phase follows a similar set of steps and extends the training receipt with the reference to the prediction sample and the result. So the model holder first sends the model and the receipt to the compute parties and then proves that the model corresponds to the commitment inside the training receipt. And the client then sends its input and a corresponding fresh commitment and proves that they are consistent. After computing the prediction, the computing parties also generate a commitment to the output and provide a signature similar as in training. And then finally, the model holder also provides a signature to make up the full inference receipt. So then when the client wants to audit their prediction, it forwards the receipt to the audit computers, which can then use this receipt to verify the inputs that the parties are going to provide to the auditing phase. So after checking the signatures of the receipt, we first verify that the client provides the correct inputs, and afterwards the model holder and the data holders also send their inputs and show that it matches the commitments on the receipt. So we now know that the inputs are consistent and that we've received all the necessary inputs to run auditing functions. So while we support arbitrary auditing functions, in our evaluation we cover 4 functions that each focus on ensuring properties related to fairness, safety, transparency, or accountability. So because our protocol is modular in the type of PPML computation, what is more relevant than end-to-end cost is to look at the overhead that our protocol introduces in order to augment the PPML pipeline with auditing. And so this overhead is primarily dominated by the cost of storing and verifying the commitments, because the receipt contains at most one signature per party, but stores commitments to the full training dataset and model. So what we really want is a succinct commitment that we can efficiently verify in MPC. So what would happen if we just use a regular commitment? Well, in that case, we'd have to recompute the commitment, but over the secret shares. And people have actually looked at this problem before in a related setting and have designed specialized hash functions for MPC. But even for those, the cost of computing them is prohibitive, already for medium-sized models, because of the nonlinearity that is inherent in these hash functions. And so what we would get is a commitment that is succinct, but a POC.check primitive that is inefficient to verify. So instead, people have looked at using homomorphic commitments to shift some of the computation from the expensive MPC protocol to local. And so this works by storing individual commitments to the elements of the input vector instead of a single commitment. And then for verification, the verifiers take a random linear combination of the input secret shares, which is very cheap, so that they only have to compute a commitment in MPC for one value rather than for all the values. And then in the last step, they locally verify that this single commitment matches the linear combination of the commitments, which requires the homomorphic property. And this approach shifts a significant amount of work to the verifiers locally, which is great. But a downside is that we now need to store individual commitments in order to be able to take the random linear combination, which results in a significant amount of storage for clients. So in our protocol, we achieve the best of both homomorphic and hash-based commitments. So we have constant storage and only a very small amount of MPC computation. And the key insight of our protocol is that instead of recomputing the commitment, we perform an equality test between the commitment and the secret shares, which should be much cheaper to do in general. So the way we do this test is using polynomial commitments, which allow the prover to commit to a polynomial in a succinct way and then generate a proof that a certain value is the evaluation of the polynomial at a certain point. And we define this polynomial by interpreting the values of our input vector as the coefficients. So in the protocol, the prover generates an opening proof for this polynomial at a point that is randomly sampled by the verifiers, and the verifiers then evaluate the same polynomial over the secret shares and open the result as well. And this is sound, because if the 2 polynomials agree at this random point, then with high probability the 2 polynomials are equal. So we do need to take care that this opening does not reveal anything about the inputs, and for homomorphic polynomial commitments, we can do this very efficiently with straightforward masking. So the benefit of this approach is that this gives us a succinct commitment to the inputs, and it minimizes the amount of work that we need to do in MPC, because all the computations related to evaluating this polynomial at a public point can be done locally by each verifier on their individual secret shares. At the same time, we shift work from the verifier to the prover using the opening proof, which can be verified typically in sublinear time and can be batched across multiple provers. So this gives us a proof of consistency that is both succinct and very efficient to verify. So we implemented a prototype of our framework on top of MP speeds and evaluated the overhead of our protocol when instantiated with different approaches to the proof of consistency. So we compare our approach with KCG polynomial commitments to the hash-based commitments and homomorphic commitments from related work. So here we look at the wall clock time of the PPML computation compared to the overhead of the consistency for tasks of increasing size. And so for training, we can see that the overhead of our approach is essentially negligible. For inference, which is a much smaller computation, we see that the overhead is roughly the time it takes to do a single inference. So this is not insignificant, but in absolute terms, these numbers are still manageable. And then finally, for the storage overhead of the inference receipt, we see that both our approach and the hash-based approach have constant storage overhead. The Peterson commitments, on the other hand, quickly become expensive, taking 5 gigabytes of storage for an inference with a CFAR10 model, and about 11 gigabytes for an inference with a BERT model. So we also evaluated 4 auditing functions, but here I'm only showing results for KNN Shapley, which is an auditing function that takes the training data set, the model, and the prediction as input, and then finds training samples that are relevant for that prediction. So looking at the related work for larger data sets, we can see that the linear MPC overhead of the hash-based commitment takes over, and that the Peterson commitment-based approach becomes much more competitive in terms of computation. For our approach, we can see that the overhead of auditing is manageable while only requiring a storage size that is constant. So where prior systems would frequently turn practical deployments impractical, the overhead of our system is basically insignificant in the context of PPML, which allows us to audit PPML systems with virtually no overhead. So in this talk, I presented a framework that extends existing PPML pipelines with an auditing phase and that achieves consistency between phases efficiently through a new input checking protocol that relies on polynomial commitments. In the paper, we also cover other aspects related to the auditing framework that I didn't get the chance to cover today. And here I leave you with some links in case you want to learn more. And that brings me to the end of my talk. Thank you very much for your attention.